This video is on section 3.2 notes, zeros of polynomial functions. So the first thing we're going to do is look at polynomial long division and synthetic division, and you'll see in a little bit kind of how both of those have their use. Typically synthetic division because it's a bit of a shortcut, but how those have their use in helping us find zeros of polynomial functions, even though it doesn't feel like it at first. So polynomial long division is kind of what it sounds like. It's long division like you might have done in 4th grade maybe, but with polynomials instead of just with regular numbers. So we're taking this, I'm going to go ahead and draw my long division, 2x to the third minus 5x squared plus 4x minus 6 divided by x minus 3. And polynomial long division feels pretty intimidating when you first do it, but it's very repetitive. So if you can kind of understand the steps and just do them over and over and be really careful with your work, then you can definitely be successful with it. So the first thing we look at is x multiplied by what gives you 2x to the third, and that would be 2x squared. So x times 2x squared is what would give you 2x to the third. Once you know what gives you this term, then you just take what you just found and multiply it by both of these. So 2x squared times x would be 2x to the third. These two things should be identical because that's what you just figured out. And then 2x squared times negative 3 is negative 6x squared. And then whenever we do long division, we always subtract those numbers. So here we're going to draw the line, and since we're subtracting both of these, I'm going to subtract, and then when I subtract a negative, it's going to change to a positive. So the way that I like to remember this is I say draw the line underneath and then change the signs, because that's what happens when you subtract. You change the signs of something. So these two will always subtract to be 0. They're always going to completely cancel out because you chose those numbers on purpose. And then these two will be something else. So negative 5x squared, positive 6x squared, that's just 1x squared. And then you drop down the next term, just like you would do in regular long division. And then we just go through the process again. That's the whole process. So we say x times what is x squared, and it's just an x. And then we take whatever we got up here and we just distribute it to both terms. X times x is x squared. X times negative 3 is negative 3x. I draw the line. I change both signs because I'm subtracting. These should always cancel out to be 0. And then 4 and 3 makes 7. I drop down the next term. X multiplied by what is 7x? That would be 7. And then I take the number on top and I distribute it to both terms. 7 times x is 7x. 7 times negative 3 is negative 21. I draw the line. I change both signs. These should cancel out because they're identical. Positive 21 and a negative 6 would be a 15. And if you were doing this in elementary school, you would just say, oh, it's a remainder of 15. If you guys remember doing that. Now we know that whenever you have a remainder, that remainder is still being divided by x minus 3, so we would just write it like a fraction. So our answer for this, if we were to divide these, is that 2x to the third minus 5x squared plus 4x minus 6 divided by x minus 3 is 2x squared plus x plus 7. The remainder is positive, so I'm going to say plus 15, which is still being divided by x minus 3. So that's how we do our division. We're going to come back in a little bit and do synthetic division when we learn the shortcut. In this next example, we're going to be taking x to the fourth minus 14x squared plus 5x minus 9 and dividing it by x plus 4. And one thing we have to be careful of when we perform these polynomial long division problems is to make sure that we have something representing each term that should be there. So if you were dealing with long division, if you had the number 1056, you would have a 0 there representing the 100th place. It would hold that position. You wouldn't just say 156 because that's 156. We're going to do something similar here. So here with the number, you would already have the 0 written in. Here, whenever we deal with polynomials, we don't have the 0 written in. The term would just be missing. So we have to put a 0 in here to represent the x to the third position. Similar to over here, we have a 0 representing the 100th position. So we can see in this problem, we had x to the third, x to the second, x, and then just a constant. Here we have x to the fourth, no x to the third, and then x to the second, x, and a constant. So we want to make sure that anytime we have something missing, we put a 0 in its place, just to make sure that we have a position for it. And you'll see why, as we do this problem, why that's going to be important. I'm going to erase this so we don't think this is part of the answer. Okay, so x multiplied by what is x to the fourth? And that would be x to the third. And then I take the x to the third and I multiply it by each of the terms, and I get x to the fourth. X to the third times 4 is 4x to the third. And this is why it's important to have that term there as a placeholder, because if I didn't have it there, then I would have incorrectly lined this up under the x squared. So you always have to have all of the places in their proper position just to make sure that you can combine like terms with like terms. So I'm drawing the line, I'm changing the signs. Those cancel out as they should. And then 0 subtract 4 would be negative 4x to the third. I'll drop down the next term. And as I go through these other two examples, as you feel yourself kind of understanding what I'm doing, it would be good for you to pause the video, try a couple steps, and then unpause and make sure that you've done those steps correctly. And do that a few times. That's what these examples are for, is to give you a chance to kind of test yourself and just make sure that you do understand the process. So x multiplied by what is negative 4x to the third? That would be negative 4x squared. Negative 4x squared times x is negative 4x to the third. Negative 4x times positive 4 is negative 16x squared. I'll draw the line, change the signs. These should cancel out, and they do. And then over here I have a positive 2x squared, and I'll drop down the next term. X multiplied by what is 2x squared? That would be positive 2x. 2x times x is 2x squared. 2x times 4 is 8x. Draw the line, change the signs. These cancel out. This gives me negative 3x. I'll drop down the next term. X multiplied by what is negative 3x? It'd be negative 3. Negative 3 times x is negative 3x. Negative 3 times 4 is negative 12. Draw the line, change the signs. Those cancel each other out. Here we have 3. And so we have a remainder of 3, which we know we're going to be writing as a fraction. So I've got x to the third minus 4x squared plus 2x minus 3 plus 3 is a remainder, which is still being divided by x plus 4. All right, x to the third minus 7x plus 5. Again, we have a missing term. We're missing the x squared term. So I'm going to make sure to put that in there. X to the third plus 0x squared minus 7x plus 5. It is possible for the missing term to be the constant on the end. Maybe the problem ends with an x, and then you have to put a plus 0 on the end. It's possible for that to happen. So just be on the lookout to see if all of your terms are represented. Whatever the highest exponent is, they should go in descending order, and then you should have a term on the end that has no variable. All right, x multiplied by what is x to the third? That would be x squared. X squared times x is x to the third. X squared times 2 is 2x squared. Draw the line, change the signs. Those cancel out. Negative 2x squared. I'll drop the next term. X multiplied by what is negative 2x squared? That'd be negative 2x. Negative 2x times x is negative 2x squared. Negative 2x times 2 is negative 4x. Draw the line, change the signs. This is negative 3x. Bring down the 5. X multiplied by what is negative 3x? That'd be negative 3. Negative 3 times x is negative 3x. Negative 3 times 2 is negative 6. Draw the line, change the signs, and I get 11. So a remainder of 11. So for all these problems, we happened to have a positive remainder, but it's possible that you could end up with a negative remainder. And the only way that would change your answer is that instead of writing plus the fraction at the end with the remainder, you would do minus if you had a negative remainder. So plus 11 because we have a positive 11 as our remainder. All right, synthetic division is just a shortcut of this same thing, and most students, once they have learned synthetic division, that's all they do. The reason that we don't teach synthetic division first is because polynomial division always works. No matter what the problem looks like, you can do a polynomial raised to the third power divided by a polynomial raised to the second power. You could do a polynomial raised to the fifth power divided by a polynomial raised to the third power. Synthetic division only works if you're dividing by basically like a linear polynomial. You're dividing by a straight line, dividing by x minus 3, dividing by x plus 5, dividing by x minus 7. That's the only time it works. And so if you're not dividing by that, even if you have a coefficient in front of the x, it makes synthetic division a little bit more difficult. But if you're not dividing by something that looks like this, then you should be doing long division. And that's why we teach you, because it always works. So for these examples, though, we can do synthetic division. So I do want to redo these same problems and show you how much easier they can be with synthetic division. So it looks weird. It's a weird process, but it's easier to catch on to. So you take whatever your binomial is that you're dividing by, and you use the opposite of the number. So I'm going to use a positive 3. And I'm just going to show you the typical notation. Usually put it in like a little box, kind of like this. And then they take the coefficients of all of these numbers. So 2, negative 5, 4, and negative 6. All right, and then the first number is just going to drop down, so I always start with an arrow, like that. So this is how I set up the problem always. So the opposite sign of this term, and then the coefficients for everything else. All right, so what we do is we do 2 times 3 is 6, and then we add these together to get 1. And you can see what's happening here. This is the 6, and this is the 1x squared. All right, then we multiply it. 1 times 3 is 3. Add these together to get 7. So here's your 3, here's your 7. 7 times 3 is 21. Add these together to get 15. There's your 21, there's your 15. So since you took something that was x to the third and divided it by something that was x to the first, that means your answer is x squared. So then you can just write x squared, x, no x, and fraction. And there's your answer. Okay, let's try this again. So I'm going to take this number, I'm going to use the opposite, negative 4. And then I'm going to use coefficients for all of these terms, making sure that I have a 0 for x to the third. So I have 1, 0, negative 14, 5, negative 9. And I always drop down the first term. Okay, so I've got 1 times negative 4 is negative 4. There's my negative 4 right there. I combine them together to get negative 4. That's right here. Negative 4 times negative 4 is 16. I combine those to get 2. There's my 16. There's my 2. I multiply those to get -8, combine them together to get -3. Here's my -8, there's my -3. -3 times -4 is 12, combine those to get 3. So there's my 12, there's my 3. So I had an x to the fourth, I divided it by an x, so that means my answer is going to start with x to the third. So I have x to the third, x to the second, x, no x, and then a fraction. Okay, this next one, I would pause the video, I'd try it on your own, and then unpause the video and see if you get it right. So -2 goes in the little box. I'm going to write my coefficients, making sure that I have a 0 coefficient for x squared. -7, +5. The first number always drops down. 1 times -2 is -2. So there's my 0, -2. And those are going to combine to be -2. -2 times -2 is 4. That combines to be -3. So you can see those numbers. -3 times 2 is 6. Those combine to be 11. So there's my numbers here. I had an x to the third. I divided it by an x, so it became x squared, x, no x, and then the fraction. All right, on the next page, we're going to look at some implications of this, but before we do that, I want to show you a little bit more about how all these things interact. So you can write this at the top of your paper if you want, you don't have to. If I was to do something with numbers, if I did 25 divided by 4, I would say that 25 divided by 4 is 7, right? Because, no, not 7, 6. Is 6 with a remainder of 1, right? Or I could say 6 1/4. So 6 with a remainder of 1 or 6 1/4. 4 does not go into 25 evenly. So if I wanted to write kind of like the inverse or the opposite of this statement, I could say that 4 times 6 plus the remainder equals 25. 4 times 6 is 24 plus the remainder of 1 is 25. You can do the same thing with these statements, just so we can make sure we understand what we've actually done here. If I say that 2x to the third minus 5x squared plus 4x minus 6 divided by x minus 3 is this, that's the same thing as saying x minus 3 times 2x squared plus x plus 7 is going to get us really close to this polynomial function, but we're going to have to add 15 to it. We're going to have to add that remainder to make sure we get all the way back to the polynomial function. So it's kind of like saying this is 25. We're doing 25 divided by 4, and we get 6 with a remainder of 1. So it's kind of like saying 4 times 6 plus 1 gives us 25. Something that is not quite a factor. It doesn't go into it evenly. We're dividing by just some random number, okay? So I want you to kind of understand the big picture. So this equals p of x, the original function. If we were to take the original function and divide by a factor like this, or divide by a binomial like this, and it ended up being a factor, then we'd have no remainder, right? Like if we took 25 and we divided it by one of its factors, we took 25 and divided it by 5, we would have a remainder of 0. That's how it works. So when I divide the polynomial function by a binomial, if the remainder is something other than 0, then it didn't go in evenly. That means it's not a factor. If it did have a remainder of 0, then it went in evenly, and it was a factor, okay? And that's important for when we turn to the next page. So the next page has something called the remainder theorem. And the remainder theorem is just kind of an interesting way to use long division to evaluate polynomials. And the reason that we learn this is because it's helpful sometimes to be able to do things without calculators and to be able to do them efficiently without calculators. This is an efficient way to evaluate a polynomial function without a calculator, if you were not allowed to use one. So for those of you taking the course online, I can't control whether or not you use a calculator. And often we're going to have even, simple scientific calculators at our fingertips, but that's kind of the purpose of this. So the remainder theorem says that if you want to evaluate a function at a certain value, you can just divide it, and whatever the remainder is, that's what the function would have been evaluated at that value. And I'm going to show you how that works using this example we just looked at. So we said, find p of 3 if p of x looks like this function, and that's the function we literally just worked with. This function right here. Here's p of x. It's the function we just worked with. So I'm just going to kind of write out this proof statement using this specific function. So if I took p of x and I divided it by x minus 3, I end up getting this as a result. Okay? So I know that p of x is x minus 3 multiplied by this part right here, 2x squared plus x plus 7, and then we just have to tack that remainder on at the end. So this is kind of like saying I had 24 divided by 4 equals 6, plus 1, plus the remainder. Now, if I wanted to plug in 3, I would just say, let me plug in 3 here, 3 minus 3, 2 times 3 squared plus 3 plus 7. And what ends up happening when I plug in 3 is that this factor in the front, 3 minus 3, ends up being 0. And 0 times anything is 0. And so this whole thing goes away. And we end up with just the remainder of 15. And so p of 3 equals 15. You don't have to memorize how that works. All you have to remember is that if I want to find out what a function is evaluated at a specific number, I can just do synthetic division, find the remainder, and that's the answer. Okay, so I'm going to walk you through this a couple times and make sure that we understand what's going on here. So this says use the remainder theorem to find p of -1. So I'm going to plug in -1. 5x to the third plus x squared minus 7. They're skipping the x term, so I'm going to have to use 0 for that. So 5x to the third, 1x squared, 0x minus 7. I drop down the 5. 5 times -1 is -5. Those add to -4. -4 times -1 is 4. Those add to 4. 4 times -1 is -4. These add to -11. Okay, so this means that if I take this function and plug in -1, my result is going to be -11. And the benefit of this method of using the remainder theorem is that I didn't have to use a calculator to get that calculation. It was pretty easy to get. And you could get this by hand. This is a pretty simple polynomial, but sometimes they're really complicated. So that's kind of the benefit. That's the reason why we care. So let me go ahead and just plug this in and make sure that I got the answer right. -1, I'm going to store as x. This is how I like to plug numbers in. So -1, I hit the store button, I'm storing, and then I hit the x button up here. -1 is stored as x, and then I'm going to type in 5x to the third plus x squared minus 7. And so what my calculator is doing is it's taking -1, it's putting it in every time I use the X button. It's -11. So that's a way to confirm. Now, when the instructions say use the remainder theorem, this is the work that has to be seen. If this is written, or you say I plugged it in my calculator, or you say 5 times -1 to the third plus -1 squared minus 7 equals -11. I mean, this is great. This is checking your work, but this is not using the process of the remainder theorem to evaluate. So this would be wrong, even though it has the right final answer. This is the work that should be shown. Or if you really like polynomial long division and you don't like synthetic division, you could show this work and show that the answer down here, the remainder, was -11, and then you'd have the work shown for the remainder theorem appropriately as well. All right, we're going to do it again. Plug in 2 to the function. We've got 1. This skips x to the third, so I'm going to put a 0 in there for x to the third. And then 3, -5, -8. 1 times 2 is 2. 2 times 2 is 4. 7 times 2 is 14. 9 times 2 is 18. So this says that if I plug in 2, I get 10. And you can always check it. X to the fourth plus 3x squared minus 5x minus 8. And I get 10. All right. The factor theorem says the number c is a 0 of a polynomial function. 0, they might also call it a root. They might also call it an x-intercept. Y equals p of x if and only if x minus c is a factor of the polynomial function. So it's a 0 of the polynomial function if it's a factor of the polynomial function. If it's a factor of the polynomial function, then p of c is going to equal 0. This is what I was talking about before. The remainder is going to be 0. There will be no remainder. It's going to divide evenly if it's a factor. So this says determine whether x minus 4 is a factor, and then if it is a factor, go ahead and finish factoring p of x. So what we're going to do is we're going to take this right here, we're going to divide it by x plus 4 and see if it divides evenly. So if x to the third minus 13x plus 12 divides by x plus 4 evenly, then x plus 4 is a factor. You don't have to write this every time. We're just writing this because these are your notes and we want to make sure we understand what we're doing. And when I say it divides evenly, I mean the remainder is 0. To divide evenly, the remainder has to be 0. So if I set up synthetic division because it's the easiest way for me to do the problem, I'm going to put -4 in the little box. Then I'm going to do 1 for x to the third. It skipped x squared, so I'm going to put 0 for x squared, then -13, then 12. I'll drop down the 1. 1 times -4 is -4. Multiply those together, I get 16, -12. My remainder was 0, so this means that this did divide evenly, so x plus 4 is a factor. Now I can go back and write what this ended up being. So x to the third divided by x would be x squared, x, no x, and then no fraction because it divided evenly. So we need to factor the rest of p of x, which is x squared minus 4x plus 3. So I'm looking for two numbers that multiply to 3 but add to -4. And those two numbers would be -3 and -1. X minus 3, x minus 1. So what this means is that if you want to look at all the factors for p of x, you would say that p of x is the original factor x plus 4, and then also x minus 3, x minus 1. And you can always check your work, make sure you got it right. So I can, on the y equals screen, I can graph the original problem, x to the third minus 13x plus 12. And then right underneath that, I can graph my factors, x plus 4, x minus 3, x minus 1. And when I graph those, there's my original graph, the original problem, and I can see the calculator's thinking, and it graphed both of these at the same time, and I only saw one graph because it graphed them on top of each other. That means that I got the problem right. So that's a good way to be able to check your work. Okay. We've got one more problem like that. It says, is x minus 1 a factor of the polynomial function? And then if it is, continue factoring. So we'll do the same process again. So I'm putting 1 in here. I just want to make sure that I have a remainder of 0 if it is a factor. All right, so x to the third, there was no x squared, which is why I put a 0 there, and then x, and then no x, the constant term. So I drop down the 1. 1 times 1 is 1. 1 times 1 is 1. -2. All right, so because there's a remainder of 0, I know that this was a factor, and so now I'm going to look at my leftovers and try to factor those. This was an x to the third. That means that this is an x squared. This is an x. This is no x. So I'm factoring x squared plus x minus 2. Two numbers that multiply to -2 but add to +1 would be 2 and -1. And so that means that p of x, if we write down all the factors for p of x, we have the x minus 1 from the original problem when they were asking us to check the factors. And then we have the additional factors of x plus 2 and x minus 1 again. So you can write it like this. This is totally fine. Or you could say x plus 2 times x minus 1 squared, because there's two of them. So either way would be fine. All right, next we're going to look at the rational root theorem. And the rational root theorem is just a way to look at a problem like this and be able to factor it. So this is 4 terms, and previously if we had a problem that had 4 terms, we would have split it in half and factored it by grouping. And if you try to split this in half and factor it by grouping, grouping doesn't work because the GCF of the first 2 pieces and there is no GCF of the second 2 pieces. But the GCFs, if you take them out, your parentheses wouldn't match. And that's what has to happen with grouping. So if we tried grouping on this, it wouldn't work. And then the way that we were factoring these other problems is they had already told us one of the factors, and then we just finished it. So here, grouping won't work, and using a factor they already gave us, or they were having us check, that won't work because they didn't give us one. So now we're going to use the rational root theorem to say, well, how do you factor something if you don't know where to start? So the rational root theorem, this is a really wordy way of saying that to find possible real roots, you take factors of this, which are going to be considered the p's. So factors of 6 are 1, 2, 3, and 6. and the factors of the coefficient. So this is the constant, this is the leading coefficient. It's the coefficient of the variable with the highest exponent. These are the q's. So the factors of 2 are just 1 and 2. So to find your possible roots, you just take the p values and the q values and you divide them, and you write down all possible combinations. And those are what your possible real roots could be. So if I look at this, my possible roots, 1 divided by 1 is 1, so positive or negative 1. 1 divided by 2 is 1/2. Okay. 2 divided by 1 is 2. 2 divided by 2 is 1. I already had that on my list. 3 divided by 1 is 3. 3 divided by 2 is 3/2. 6 divided by 1 is 6. And then 6 divided by 2 is 3, which I already had on my list. Okay, so these are possible roots. These are intercepts. I don't know if they actually go into this or not. The way that I check it, in theory, is I would do synthetic division with all of these numbers until I found one that gave me a remainder of 0. And this is where I'm going to let you guys cheat because I'm not a jerk, okay? I understand that doing synthetic division with every single one of these is a tedious process. So I am okay with you taking these and saying, well, I know that doing synthetic division and plugging these numbers in to see if they equal 0 or not, I can do that a little bit faster on my calculator if I just plug the numbers in. I understand that. The purpose of this work is to say, hey, what if you didn't have a calculator and you couldn't just graph it to find out? So that's kind of the purpose of this whole section, is what are some of the things that we can do to find zeros or x-intercepts of the graph without graphing. Having a calculator in your hand defeats the purpose of learning some of this section. However, I'm going to save you some time. So if we want to check and see what the possible roots are, I'm not going to graph this. I'm just going to start taking these numbers and plugging them into the function to see if they equal 0. The one that has a 0 would then have a remainder of 0 if I divided it, and that means it is a factor. All right, so I'm going to go through. I'm just going to start with positive 1. That's negative 6. I'll try negative 1. And I'm going to go up here and I'm going to copy paste this. And when I copy paste it, it's going to plug in my new x value. Negative 1 is 12, so it's not positive 1, it's not negative 1. Now I'm going to try 1/2. Copy paste it. 1/2 is 0. That means I just found one of my x-intercepts or one of my roots. So x equals 1/2 is one of them. All right, so I'm going to do synthetic division, 1/2. I don't have enough room down there. I'll do it over here. So 2, negative 3, negative 11, 6, 3, 2, 1, none, okay. 2 times 1/2 is 1. Negative 3 and 1 is negative 2. Negative 2 times 1/2 is negative 1. This is negative 12. Negative 12 times 1/2 is negative 6. This is 0. So this is good. I just confirmed 1/2 is one of the roots. So this gives me x to the third divided by an x. This gives me x squared, x, and 12. So if I take this quadratic and I solve it for x, then I can get the other roots. I can get the other x-intercepts, the other zeros. So when I start to solve this, the first thing that I notice is that there's a GCF of 2. I'm going to go ahead and just take that GCF of 2 out. So I'm going to say 2 x squared minus x minus 6. And then I'm going to go ahead and factor this if I can. If you can't factor it, then you're going to use the quadratic formula to find your other answers. So -6, -1. Two numbers that multiplied and made -6 but add to -1 would be -3 and +2. All right, so notice the instructions did not tell me to factor the problem. They asked me to find the real roots, the imaginary roots. So if they asked me to factor the problem, then my factors would have been not p of x this time, f of x. I would have said that f of x was 2, and then x minus 1/2, x minus 3. Let's do, oops. Okay, so if they said they wanted the factors, this is what I would have written. They didn't. They said they wanted the roots. So the roots are 1/2, +3, -2. And I was able to find that because I looked at the possible roots first. All right. For the next one, find all real and imaginary zeros. All right, so here is my p-values. 1, 2, not 3, 4, not 5 or 6 or 7, 8. So these are all the factors of 8, all the numbers that divide into 8 evenly. Q, 1 and 3. Those are all the numbers that divide into 3 evenly. So our possible roots. 1 divided by 1 is 1. 1 divided by 3 is 1/3. Oops, I was going to write 3. 2 divided by 1 is 2. 2 divided by 3 is 2/3. 4 divided by 1 is 4. 4 divided by 3 is 4/3. 8 divided by 1 is 8. 8 divided by 3 is 8/3. Okay. So again, if I was doing this problem technically the way that I should not pick up a calculator. I should take all of these and do synthetic division with every single one until I found one that had a remainder of 0. I'm not going to force you guys to do that. If you want to plug them into the equation until you find one that gives you 0 as an answer, that is totally fine to save time. Okay, so I'm plugging 1 in. I'll plug in, oops, -1. So it's not 1 or -1. I'll plug in 1/3. It's not 1/3. Plug in -1/3. It's not -1/3. Plug in 2. Plug in -2. Plug in 2/3. Two-thirds is it. Okay. And I want to show you guys what it should have looked like if I was actually doing this work. So this was problem number 1. I think on problem number 1, that was the first one I plugged in when I did it by synthetic division. But here's the second one. When I did this one using synthetic division to plug in all the numbers, this is how I did it before I found one that had 0 as a remainder. So in theory, you would say, here's my possible roots, and then you would have all this work. And then once you got to one that had a remainder of 0, that's when you could continue on with the problem. So this is in theory what you should be showing for these. I'm not going to require it. I'm not going to require it on a test either, because I understand that feels like a ridiculous request. Okay. I'm not saying it's ridiculous. I'm saying I understand if it feels ridiculous. Okay. So let's go ahead and do 2/3. The reason we're doing it with synthetic division, even though we know that the remainder is going to be 0, is because we do want to know what that leftover polynomial is so that we can continue factoring it and solving it. So I know this remainder is going to be 0 already. I know this is the one that goes in. I just need to see what the rest of the answer is. So 3 times 2/3 is 2. That's -6. -6 times 2/3 would be -12 divided by 3, 4. -12. -12 times 2/3 is -24 divided by 3, that's -8. And then there's your 0. Okay, so x to the third, that would mean that this is x squared, x and no x. And to solve this, I can factor the 3 out. We have a GCF of 3. And there's nothing that multiplies to -4 and adds to -2. This problem is not factorable. So we're going to have, we could still have some real roots, but they would be decimals. I'm going to have to find them using the quadratic formula. Or it's possible we might have some imaginary roots, imaginary zeros, since we're about to use the quadratic formula. So I'm going to have -b plus or minus b squared minus 4 times a times c divided by 2a. B squared minus 4 times a times c, 20. Okay, so these are not imaginary roots. They're just going to be real roots, but they would be decimals if we didn't leave them in radical form. Square root 20 is root 4 times root 5. That's 2 root 5. And then there's a lot of 2's we can cancel out. I can't touch the root 5, but all these 2's, just leave 1's behind. Okay, so my answers are 2/3. And then 1 plus root 5 and 1 minus root 5. 1 plus root 5, 1 minus root 5. Okay. Last problem. The p's. 1, not 2, 3, not 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 3, 5, 15. Q is 1 and 2. Okay, so our possible roots, 1 divided by 1 is 1. 1 divided by 2 is 1/2. 3 divided by 1 is 3. 3 divided by 2 is 3/2. 5 divided by 1 is 5. 5 divided by 2 is 5/2. 15 divided by 1 is 15. 15 divided by 2 is 15/2. So those are all of our possible roots. I'm going to take them and start plugging them into the function to see which one gives me 0. Okay, so it's not +1. It's not -1. It's not +1/2 or -1/2. It's not +3 or -3. +3/2. Okay. All right, so 3/2, 2, -11, 22, -15. All right, 2 times 3/2 is 3. -8 times 3 over 2 would be -24 over 2, so that's -12. 10 times 3 over 2 would be 30 over 2, which is 15. Okay, so we have x to the third. That leaves this as an x squared. X, no x. I can take out a GCF of 2. So two numbers that multiply to a +5 but add to a -4. Your only options for +5 are +1, +5, and -1, -5. And neither one of those add to -4. So this is another quadratic formula problem. So we've got -b plus or minus b squared minus 4 times a times c over 2 times a. -4. So we have 4 plus or minus 2i divided by 2. And both of those are divisible by 2. This would be 2 plus or minus 1i, and then divided by nothing. Okay. Two plus or minus 1i. All right. And on this sheet, I showed again, if you were doing it the synthetic division way, this is all the work you might have shown on your way to trying to find the actual 0 that worked for the problem. So if we were truly doing it the way it should have been done, we should not have used a calculator at all, and we would have done this, and then we could have done the computations for the quadratic formula without a calculator. So it can be done, but I'm okay with you guys using a calculator as long as you can show this way that you understand the process. So on a test, this is the work that I would expect to see.